All right, good morning, everybody. So I am on the Nanolab 600i here, and I have to final thin a lamella, and I wanted to share this with you because there's been some updates to this since the last video that I did with this microscope a long time ago, and so I wanted to go over this with you. So I've already got the ion source warmed up and the SEM and the SEM beam on as well. We'll go ahead and zero the beam shifts, got the mags coupled, and zero the beam shift here, and I have the scan rotation for the FIB set to 180, which is how I prefer to do this. And you can see here in the CCD quad that I've got the TEM grid holder loaded. I have a stored position for the grid that I'm using, so that corresponds to grid number 3. So I'm going to go ahead and move to that. Okay, and then we're going to find our sample here. So a little bit off. I'm pretty sure, no, that's not it. No. Okay, so it's this guy right here. Okay, so I'm gonna go ahead here, focus, and then I'm gonna adjust my stage tilt till I'm flush or edge on, which is about, it's about 0. So we'll just leave it there to make it easy. And then I'm going to align the grid left to right. So you can do stage XT align feature. Make sure you have this set to horizontal, and then you want to drag from left to right. And then click finish. And there we go. So now as far as the SEM conditions here, I've seen some different ways to do this where people like step down the voltage. I prefer to just leave it at 2 kilovolts the whole time, but you generally want to use like a lower current, not up here in this several nanoamp range. I'm going to leave it at 0.17 for now. The reason for this is that you're going to get a more accurate image of your lamella this way because your current is lower, and you're going to cause less contamination as well. But of course, since we're fibbing it at the same time, a lot of that contamination is just going to end up, burning off anyway. So let me go ahead here, move it to 4 millimeters, and we'll go ahead and set concentric. This is a trick I learned. Well, one of the FSEs told me. He said instead of tilting 2652, he said just tilt 1052 instead, because you have what's called the horseshoe with the tilting, so that gets you a bit more of an accurate result. So the sample is strontium titanate instead of silicon. So that's part of the reason I wanted to do this, because strontium titanate is a more challenging material to work on than silicon because it's harder. The removal rate is about half that of the silicon. So I'll discuss some of the mods that we do with the material file to account for this. I don't have a material file for strontium titanate. I have one for silicon carbide, and actually the sputtering yields for silicon carbide are basically the same or very similar to strontium titanate, and the hardness is very similar, so I actually just use that file instead. But I'll go over that with you here in a minute. So we'll go ahead and check the crossover. Now, what I actually did with this lamella, unfortunately, is I already did one milling step. So yesterday evening, I was trying to final thin this lamella. I was able to thin one side, which corresponds to the bottom here in the SEM image. And then I relative rotated 180 to do the other side, but I couldn't get to the same tilt because of a touch alarm, because in the UMB I had a stub loaded. So you know, at that point I was just frustrated, so I stopped and I took out the stub, so we shouldn't have an issue tilting to the angles that we need to tilt to. But I already did one cut to the bottom here. I'm gonna do the same exact one on the top side here, so you'll see exactly what I did. All right, so we'll go ahead and adjust this here. As far as FIB, the PT protection, I did half a micron of E-beam PT, and then I did 1 micron of FIB PT. Okay, so that looks good right there. Now I may drop the current down when we get to like below 30 kilovolt cleaning or thinning, but I'm just gonna leave this now. All right, so I'm gonna tilt to 52 degrees. Okay, and that looks good right now. So now the first cut that I did was I over tilted by 5 degrees. Okay, so again, 52 is our parallel for the fib, so we can go back and forth from there. So I'm going to go to 57. Okay, I can bring this up just a smidge more. And then I'm going to unpause do I have beam on? Yes, I do. I'm going to unpause this. If you hold shift and left click and drag, you can use your mouse to shift the image. So I already cut the, so again, remember this is scan rotated 180. So I already cut the top surface sidewall in the fib, which is the sidewall that we're seeing in the SEM right now, okay? So I'm gonna do the same thing. So this was the same setting. This was 3 nanoamps at 30 keV, and now I have an application for silicon carbide, which again is basically interchangeable, at least in my opinion, with the strontium titanate. So this was the cleaning cross section. You can see here in the advanced tab, this is the removal rate, the volume per dose. But the big difference here is because this is harder, I'm using now 90% for the overlap. Okay, so generally speaking, you want to do that when your material is harder. Okay, so now what we're going to do is we're going to relative rotate 180, and we're going to do the same thing on the other side of the lamella. So you want to make sure in your navigation tab for your coordinates you have compucentric rotation checked. And then for stage, you want to have enable stage safe stage moves checked, and then you can do relative rotate 180. Whoops, let's not do 1480. Okay, now there's an alignment you have to do to align the compucentric rotation to ensure that this works, which is very easy to do. Basically, you need to load a stub at approximately the center of the stage and bring it to eucentric, and then basically the stage is going to rotate continuously and you're going to align to the center of rotation. I've already done it. I don't have a good sample in here to do it right now, but it's fairly straightforward to do, but you want to make sure to do that. So if you can see, right, we're right back on the lamella here, okay? So I'm going to go ahead and refocus that. And we're still seeing this. Okay, perfect. So I am going to now change the scan direction from top to bottom. Use 4. And I'm gonna cut through. So the way I actually welded this to the grid, I actually put a whole strap along the bottom instead of just the corners, which I find actually is giving me some better results. Let me cut this down to 9.5 here just to be safe. And we'll go with that. Okay, we can move this down just maybe a smidge more. But again, we're 5 degrees over tilted right now, okay? All right, there we go. Because the current's low, live imaging is not gonna really be effective, so we can use spy mode here. So you can uncheck this here and then unpause the SEM. And so every line interval, it will take a snapshot based on what your dwell time is here. Apologize, we're back to crappy cell phone video, but there's no way to do screen capture on this system, at least conveniently, because it is running Windows XP. Okay, so this dark line here, this is a conductive protective coating, just FYI. So I'm gonna cut this until I see the strap start to even out. So this is the really, if you can do this now, we have the stability to do this on this stage. I demonstrated this relative rotate technique on the FIB. The problem with that is the stage doesn't have the same level of stability, so there's movement when you're cutting specifically in this direction. But with this stage, which is piezo enhanced, and we have the UMB, we don't have that problem, and the stability is really good. So this works very effectively, the relative rotate approach. I'm going to keep my mouse on the stop button here. Okay, we're starting to eat the bottom, so that's perfect. All right, so now we are going to we're going to drop our current down to 1 nanoamp, and we're going to do another relative rotate 180, but we're going to change the over tilt angle a little bit here. Okay, so what are we gonna do here? Let's change this to actual. So let's go ahead and we'll leave this at +5 for now, and I think we'll probably drop it when we well, no, let's go ahead, we'll drop this down, we'll drop this to 3. Okay, and then we can use our shift. Yeah. Hate it when it does that. Come on. Shift, bring it back. You can focus and stigmate here in your FIB image as well. When we get to the low kilovolt stuff, we're gonna do some direct alignments here. I'm gonna cut the Y dimension down by half a micron. Okay, and we'll go ahead and go with this. Oops, somehow I don't know how, I accidentally shifted the image a little. That's okay. You can do the same thing in the SEM image here. Hold shift and then left click and drag, and you can drag that image around. So basically I'm gonna do this till we cut through the bottom here. You can see this is kind of working through. There you can see very clearly the protective coating, E-beam, and then the FIB coating. Generally speaking, with the harder material, you want to use a larger overlap. In general, this is what I tend to find. All right, so I'm gonna zero the shift here, and we're gonna cut the same thing, but from the other side. So we'll do relative and 180. Oops, sorry. You can't see this on the camera right now, but one of the things I'm doing is I'm taking notes here about the prep, okay? So I'm actually documenting all the cuts that I'm doing here and what I did each time, so I can remember what I did with you know, a degree of specificity here. So what I'm doing is I'm keeping track of like the overlap and the over tilt and the current and the patterns and yeah, all that good stuff here. Okay, we'll drop this down by another 1/2 of a micron, and we'll cut the same thing here. So same thing, we're gonna cut this until we see the bottom start to wear through. So the current's being dropped by about, well, it's a factor of 3 each time. So that's kind of the rule of thumb with like polishing damage, right? Is you reduce your grit by a factor of 3. So this method is actually based on a paper that was published a number of years ago by Schaffer. I'll put a link in the description box so you can see. But this is where actually I found out about this relative rotate method, and I have incorporated this as much as I can because this is really just great to ensure that you're getting what you want to get or seeing what you want to see with your lamellas, okay? All right, so we're through the bottom there. Okay, perfect. So I'm gonna do another relative rotate here. And we're gonna go to 0.3 nanoamps, and I'm gonna drop my over tilt down a degree. We'll go to +2 degrees. I'll adjust that once we're done moving. And I'm also gonna drop my Z down a little bit. Okay, so we'll go to 54, so that's +2 degrees. You got to be careful when if you're going to stigmate your FIB image, you don't want to use reduced area over your lamella. You could use it over part of the grid, but I wouldn't do it over the lamella, certainly. Let's drop it down to, let's see, so this is going to be a little bit longer, so we can drop this down by a whole micron, and we'll leave it there, and we'll drop this to 3 because our lamella is getting not as tall, and there we go. You can increase your dwell time here. The problem with that, of course, is that it's gonna, make your prep longer because it takes longer to do each snapshot. But again, right? That's you want good results. Sometimes they take longer. Now the bottom's looking pretty gnarly, but we don't really care about this. I mean, this is actually very tall as far as lamellas are concerned. If we actually draw this and then we apply tilt correction for cross section, yeah, so this is, you know, pretty tall as far as lamellas. You know, in this case, we only care about the surface area or the near surface area. Okay. So these over tilts, you know, obviously this is material dependent. Generally speaking, the harder the material, the higher the over tilt you can use. Like I actually found with sapphire, I kind of based this on a sapphire sample, but in that case, I'm going to stop it right there, and we'll rotate relative 180 and do the same thing from the other side. But the sapphire, of course, has a lower sputtering yield than strontium titanate does. We'll drop this down again to 6.5 and we'll cut this top side. Now after this cut, we will we'll drop the voltage to 8 and we will proceed from there. Okay, we'll leave that there. We're chewing the bottom, that's okay. This is looking really good though. So far, of course. There's still time to mess it up. But we still have basically the entire PT strap intact, which is good. Alright, so let this run here. Alright, we'll stop it there. Okay. Alright, so I'm going to drop the voltage now to 8, and we'll leave it at this current. And let me take a look here. Okay, so we'll keep the plus 2 degrees, and we'll relative rotate again, of course. And I'm going to drop the Z down to 2, and we'll have to do some direct alignments to our FIB image here, of course. Okay, so we can do L2 modulator here. That actually looks pretty good, so we can leave that alone. So the only thing left is to focus and stigmate. Okay, that looks reasonable right there. All right, so we'll cut our dimension down again. And now because of our, because we've reduced the voltage and the current, our removal rate's gonna be much slower now. But we'll leave it right there. And we can probably be, yeah, that's fine right there. I'm not gonna go all the way to the edge, the bottom edge there. All right, we'll leave that there. Now, because the current's a lot lower, we can probably now turn off spy mode and just live image this. And just turn on, say, an average filter, maybe not quite that many frames. And we don't care about this, right? So don't worry about that. We still got about 5 microns of material here, so we're fine. We still have to do this at 5 kilovolts, so there's no issue here. Okay, we'll relative rotate again. Drop that down a little more. So we got to do 5 and then 2 kilovolts, and so I'm going to do the 5 at the 2 degrees as well. The 2 will be at plus 5 degrees. So we're going to basically almost endpoint at 5 kilovolts. Because you don't want to do a lot of thinning at 2, because you're going to potentially introduce a lot of curtaining, because the curtaining gets worse as the voltage goes down. So you want to try to do, minimal 2 kilovolts. We can make an adjustment to the overlap, so I will increase the overlap manually to 95% for the 5 and the 2 kilovolt thinning. So, and that's very easy to do. I'll show you how to do that here. Alright, go ahead and, well, it's almost done here, so we'll just leave it. Okay, so we'll drop this down to 5, we'll leave it at 48, do the relative rotate again, and we'll change the overlap to 95%. Alright, so your image quality is of course going to look crappier here as the voltage goes down. Got to align the quad here. That looks reasonable. Okay, and then we'll go. All right, we'll drop this down to maybe 4.5. Let me take a look here. Okay, we'll leave that at 2, that's fine. So again, your sputtering yield is going to go down further at 5 kilovolts. Right there. So what we're going for here is basically just a little bit of platinum on the top here, and that's how we know that it's thin near the the top here. At least that's one approach. That's the approach that I use personally. So it's definitely thin down here at the bottom, but we're trying to get it thin like up here. So. we still have all of that E-beam platinum there. I mean, if we measure this, it should be about, yeah, so it's, I targeted half a micron. It's actually appears to be a little bit more than that. All right, so I think let's stop right there. We'll do the other side now. And hopefully this will be able to endpoint this. You can tell there it's getting quite thin though, which is, hey, that's the name of the game, right? So if your snapshot, you can just manually increase the, I mean, that helps a lot at the lower, actually there we go, we can see that a little bit better. All right, let me drop this down to 4. Right there. Make sure we're goops. Yeah, so I took another snapshot. That's okay. All right, we'll leave it there. Okay, here we go. Of course, if we're not, as thin as we need to be, we can repeat this on the other side. We don't, again, like I said, we don't want to go very hard with the 2 kilovolt beam. That's, again, not a good idea. If you're going to do 2 kilovolts, you want that to be minimal and just very brief, so you don't cause a lot of curtaining. Okay, so now we're getting there. So again, we're gonna stop this. Let me get just a little bit of platinum there on the surface. All right, let's stop it there. And we will go ahead now. We'll drop this to 2 and 8.9, so not very much at all. And we'll relative rotate. And we're going to go now to the rectangle. And we're going to change our over tilt to +5 degrees. Again, I'm going to put the overlap back to 95%. And our image actually looks not too bad, believe it or not. that's off, of course. Okay, so this becomes trickier to do. Now, let me go ahead here and, okay, so we're gonna go back to 57, which is plus 5 degrees. And again, you don't have much here in the way of current here. So it's tough to stigmate with this. Looks like the stigmation center might be off a little bit, but that's okay. At 2 kilovolts, definitely the effect of the vacuum will become very apparent. So you need good vacuum for effective low kilovolt imaging, especially at 2. Okay, there we go. That looks all right. We'll keep that at 4, and I'm not going to use a specific depth. I'm going to just monitor this manually. Keep the width at 4. And we want to go the whole width of the sidewall there. Keep in mind the beam is, the beam is much bigger than the area. It's not confined to just the rectangle. All right, there we go. So we'll go here and watch this. Okay, so we're watching the platinum here. You can watch the accumulated depth just for, yes, we're seeing it thin. Stop it at about 0.1 there. Okay, stop it there. And we'll rotate and do the other side. Looks good. Refresh it one more time. Okay, there we go. All right, so again, I want to make sure that we leave just a little bit of platinum there on the surface. So I'm going to stop this before it gets there. See, it's going down though, which is good. That's what we want because we know it's actually thinning. All right, I'm gonna stop it there. Okay, so there we go. All right. So now that film should be nice and thin there. That's what we're interested in. Let me tilt back to 0 degrees here. maybe get a gauge on. Now we don't want to do any more FIB imaging. Let me drop the current down a little more here so we don't risk contaminating. Again, we're going to plasma clean this anyway before we, STEM it, so keep that in mind, of course. Yeah, that looks really, I mean, it's tough to tell. We probably got some bending, but that should be good to go. Just off the cuff, I mean, it's tough to make a measurement here in terms of what that might be. I mean, if we do, yeah, it's probably thin. I mean, it's probably thinner than that, depending on where we are here. So, a few tens of nanometers. And again, that's because we're looking at a projection of this, right? The actual thickness, near the area of interest, again, could be, quite thin. So, but there we go. So we'll go ahead and stop that. And that is an updated approach for final thinning. So hopefully I gave you some, new ideas for what you can do, for approaches you can take. Maybe this will, get you thinking, some new ways to do things. I'll put the, links in the description, of course, and hope you're having a good day, and I'll talk to you again soon.